As we delve deeper into chemistry, we will need to use quantitative arguments. To prepare for what is to come, we will now talk about numerical data, about how it is obtained and used in science. Science often deals with numbers that are very small or very large. For instance, we said that the size of a hydrogen atom is 1 billion times smaller than the size of an apple, and that its mass is about 60 septillion times lighter than an apple's. Writing out numbers of that magnitude explicitly is inconvenient, so we use what is called scientific notation. To understand how scientific notation works, we first need to understand the powers of 10. A positive power of 10 denotes a product of as many tens as the number indicating the power, called the exponent. So 10 to the third power equals 10 times 10 times 10, and that is 1,000. 10 to the second power is simply 10 times 10, or 100, and 10 to the first power is simply 10. We can see that a positive exponent is the same as the number of zeros that follow 1. 1,000, or 10 to the third, is 1 followed by 3 zeros. A negative power of 10 is 1 divided by 10 to a positive power. For example, 10 to the power minus 3 is 1 divided by 10 to the third power, or 1 divided by 1,000, or 1 1,000ths. A negative exponent is the same as the total number of zeros that precede 1, including the zero before the decimal point. Finally, by convention, 10 to the zeroth power is 1, that is 1 not followed or preceded by any zeros. We can now realize that any number could be rewritten as some number between 1 and 10 multiplied by some power of 10. For instance, 300 is 3 times 100, 3 times 10 to the second power. 350 is 3.5 times 100, or 3.5 times 10 to the second power. And 354 is 3.54 times 100, or 3.54 times 10 to the second power. This notation, where a number with one non-zero digit before the decimal point is multiplied by a power of 10, is called scientific notation. The power of 10 in it is called the order of magnitude. When we say tens, hundreds, or thousands, we are referring to the order of magnitude of a number. The scientific notation is convenient for writing very large or very small numbers. Consider length scales. The largest length scale that we can think of is the size of the observable universe. It's about 5.35 times 10 to the 23rd power miles. This is about 1 million times larger than the size of our galaxy, the Milky Way, which is about 5.88 times 10 to the 17th power miles across. A whole new perspective on how exactly far a galaxy far, far away might be. Our galaxy, in turn, is about 3.16 billion times larger than the solar system, which is about 1.86 times 10 to the 8th power miles in diameter. These very large numbers are much more conveniently written in scientific notation than if one were to write them out explicitly. Try it. The Sun is about 200 times smaller than the solar system, and the Earth is about another 100 times smaller than the Sun, about 7,920 miles in diameter. At these scales, writing out distances in miles explicitly becomes practical. Now, what happens if we go to even smaller lengths? The height of an average person is almost 10 million times smaller than the diameter of the Earth, about 5 to 6 feet, or 0.001 mile. The size of a fruit fly is another 500 times smaller, about 1/8 of an inch or 2 times 10 to the minus 6 power miles. Atoms are about 20 million times smaller than fruit flies, with sizes on the order of 10 to the minus 13th power miles, and atomic nuclei are still 100,000 times smaller, with sizes on the order of 10 to the power minus 18th miles. Now, you might think that no one would really measure the height of a human or the size of a fruit fly in miles. One would use feet or inches instead. Why not just use parsecs to measure the sizes of galaxies and angstroms to measure the sizes of atoms? However, if we want to compare the sizes of two objects, we need to express these sizes in the same units. If we know that the Earth is 7,920 miles across, and an average human is 1 times 10 to the minus 3rd power miles tall, we can determine how much larger the Earth is than the human by simply dividing the size of the Earth by the size of the human. Practice this by determining, for instance, how much bigger the Sun is than a fruit fly. If we had the diameter of the Earth in miles, but the height of a human in feet and inches, we would first need to convert both quantities to the same units. How does one perform arithmetic operations with numbers in scientific notation? If two numbers need to be added or subtracted, the number that has the smaller exponent must first be rewritten so that it has the same exponent as the number with the larger exponent. For instance, if we need to add 4.234 times 10 to the 15th power and 3.2 times 10 to the 13th power, then we need to first rewrite the number with the smaller exponent, 13, to have exponent 15. Because the difference between the exponents is 2, we simply multiply and divide 3.2 times 10 to the 13th power by 100, or 10 to the 2nd power. 3.2 times 10 to the 13th power is 3.2 times 10 to the 13th power multiplied and divided by 10 to the 2nd power. This operation didn't change the value of our number because we multiplied and divided by the same number, 10 to the 2nd power. We now regroup the terms as follows. 3.2 times 10 to the 13th power times 10 to the 2nd power and divided by 10 to the 2nd power is 3.2 divided by 10 to the 2nd power multiplied by 10 to the 13th power times 10 to the 2nd power. Let's first look at the first parentheses. If we divide 3.2 by 100, we will get 0.032. In the second parenthesis, we are multiplying 10 to the 13th power, a product of 13 tenths, by 10 to the 2nd power, a product of 2 tenths. Therefore, altogether, we have a product of 15 tenths, or 10 to the 15th power. In general, a product of 2 powers of 10 is a power of 10, with the exponent that is equal to the sum of exponents of the two terms. So now we can rewrite our product of the two parentheses as follows. 0.032 times 10 to the 15th power. Once we have done this, we can add our two numbers, 4.234 times 10 to the 15th power and 3.2 times 10 to the 13th power, which we found is the same as 0.032 times 10 to the 15th power. And to do this, we just add the numbers that are in front of the powers of 10 and keep the powers of 10 the same. 4.234 times 10 to the 15th power plus 0.032 times 10 to the 15th power is 4.234 plus 0.032 times 10 to the 15th power. And that is equal to 4.266 times 10 to the 15th power. If your answer had more or less than one non-zero digit before the decimal point, you would convert it back to scientific notation by multiplying and dividing your answer by the same power of 10, similarly to what we have done for our second summand. If two numbers need to be multiplied or divided, then you need to multiply and divide the numbers that precede the powers of 10 and multiply or divide the powers of 10 separately. For instance, if you need to divide 4.234 times 10 to the 15th power by 3.2 times 10 to the 13th power, you could do it as follows. First, you write a ratio of the two numbers. Then you regroup the terms. First, in the first parentheses, you will have the ratio of 4.234 and 3.2, and in the second parentheses, you will have a ratio of 10 to the 15th power and 10 to the 13th power. So we are dividing a product of 15 tens by a product of 13 tens, and that is a product of 2 tens. Everything else cancels out. So our final answer then is the ratio in the first parentheses estimates to 1.323125, and that is multiplied by 10 to the second power that we get from the second parentheses. Here we have used the fact that in the second parentheses we have a product of 15 tens in the numerator and the product of 13 tens in the denominator, so 13 tens cancelled out and only 2 tens in the numerator are left. In general, a quotient of 2 powers of 10 is a power of 10 with the exponent that is equal to the difference between the exponent of the dividend and the exponent of the divisor.